Right, the periodic table. So, where would we be without the periodic table? This is it. This is all the information you'll ever need about the elements for IGCSE, A-level and beyond. Well, more or less. This is just a basic table. Let's have a little look at some of the characteristics. Obviously, we've got period numbers down the left-hand side. We've got group numbers along the top. And we have only the proton number or the atomic number in the boxes. We don't have the mass numbers. Okay, so what can we glean from the periodic table? Well, it's a way of organizing all of the elements in the universe and some that don't naturally occur. Remember that only elements up to uranium 92 are naturally occurring elements. After that, they are synthetic. They're made in the laboratory and are often very unstable and only hang around for a couple of milliseconds. So we've got the periods down the side. We've got the groups along the top. They're going to tell us something about the valency and the electrons in each of the elements or the atoms of the elements. And also they're going to help us to classify elements as metals and non-metals. So let's have a look at that in a bit more detail. The period tells us how many shells or energy levels of electrons that we have around the nucleus. So we look at the number down the side and it tells us immediately how many energy levels, how many electron shells each particular atom of the element has. So if I look at something like magnesium, it's in period 3, so it's got 3 shells. Hydrogen, period 1, it's got 1 shell. Okay, that's fairly straightforward. So I'll have a little bit of practice of that. Magnesium, it's in period 3, so it's got 3 energy levels. There are a couple more spaces for you to fill in that table. Okay, so boron is in period 2. It's got 2 energy levels, 2 shells. Calcium's in period 4. So it's got 4 energy levels, and you get the picture. The group of an element gives us the number of electrons in the outer shell, the valence shell, the outer shell. So we have here, look, 1, 2, Roman numerals. Ignore the transition elements because it's more complex. 3, 4, 5, 6, 7, and then group 0. The number of valence electrons tells us about reactivity and the characteristics of that particular element. So let's have a look at groups of the following elements and the number of electrons. If I take, for example, sodium, I know it's in group 1, it's here, and it's got 1 valence electron. It's got 1 electron in the outer shell. You can fill the rest of that table in. Shouldn't take too long. Aluminium's in group 3, so it's got 3 electrons in the outer shell. Oxygen's in group 6, 6 electrons in the outer shell. Argon is in group 0, so it's got 8 electrons in the outer shell. Valency. So, the valency of an element or an atom is the electrons that have to be gained or lost and sometimes shared to achieve a full outer shell. And remember, the point of this is that they're looking for stability. The atoms need to get a full outer shell to become more stable. a full outer shell is a stable electronic configuration. So the period will tell us about the electronic configuration of an element, and so we can work out its electronic configuration, and also by doing that we can work out its valency. You should be able to, at IGCSE, be able to give the electronic configuration of all of the elements up to calcium, 20 electrons. So lithium electronic configuration is 2, 1. This is revision from last year. It's got 2 electrons in the first shell, 1 electron in the second shell, so 2, 1, and its valency is 1. Lithium would lose 1 electron to get a full outer shell. Have a go at the other ones in the table. Potassium, electronic configuration 2881, has again got a valency of 1 because it's in group 1. It would lose that electron. Sulfur is in group 6, here it is, and because it needs to gain 2 electrons to get a full outer shell, its valency is 2. And carbon is kind of in the middle, isn't it? So carbon electronic configuration 2, 4, and it can gain 4 electrons to get a full outer shell. It's got a valency of 4. It will not lose 4 electrons to form a carbon 4 plus ion because that's too many electrons. It would require too much energy. And whether an element is a metal or non-metal, or we can deduce that from its position in the periodic table. So generally the left-hand side are where the metals are found, and the right-hand side are where the non-metals are found. And in the middle, there's like a step down, and along that step, you get something called semi-metals or metalloids. Okay, so we can start to discuss something called metallic character. Metals lose electrons to form positive ions, we know that. They react with oxygen generally to form basic oxides. Metals react with non-metals to form ionic compounds. And some examples would be, for example, potassium would lose 1 electron to form a potassium ion. Okay, it's a very obvious metal. It readily loses that electron to form a potassium ion. So this whole thing about losing electrons to form positive ions is very important with metallic character. The more tendency it has to do that, the more metallic it is. Calcium obviously would lose 2 electrons to form Ca2+ because it's in group 2. You can stop me if you want to try the rest. Aluminium loses 3 electrons. Now there's 2 examples here of iron, because we know that iron has a variable valency. It can lose 2 electrons to form Fe2+, or it can lose 3 electrons to form Fe3+. Non-metallic character is essentially to do with the elements gaining electrons or somehow achieving a greater share of electrons. So if they gain electrons, they form negative ions. They're non-metals, they gain electrons, and they form negative ions to get the noble gas electronic configuration. So chlorine, for example, if we take a chlorine atom, you know that chlorine usually goes around in packets of 2, a chlorine molecule, but we'll simplify it here. A chlorine atom would gain 1 electron to make a chloride ion. An oxygen atom, 2 electrons to form an oxide ion. A bromine to form a bromide gains 1 electron, and a nitrogen to form a nitride gains 3 electrons. So this is an example of non-metallic character. They gain electrons to form negative ions, and a full outer shell. The other possibility is that they could share electrons. They form covalent bonds and they get a share of electrons. Okay? Now, metallic character decreases as you go across the period, as the group number increases. So as you go from lithium, sodium, aluminium, silicon, its metallic character or their metallic character is decreasing. And then you get to what's next? Phosphorus, sulfur, chlorine, argon. The metallic character has completely disappeared and they've become non-metals, haven't they? So the metallic character decreases across the period. Let's have a look at period 3. We can say that these three are without a doubt, sodium, magnesium, aluminium, without a doubt they are metals, aren't they? We'll leave silicon for a second. These 4, phosphorus to argon, are non-metals. And then silicon falls into that little fuzzy overlap in the middle, where sometimes it acts like a metal, sometimes it acts like a non-metal. So we could call it a metalloid or a semi-metal. Let's go back to covalent bonding here, and let's remind ourselves how to draw the bonds formed between these non-metals in order for them to get a better share, a bigger share of electron density, of electrons, to get closer to that electronic nirvana of a full outer shell. So carbon dioxide, ammonia, ethene, and hydrogen chloride are 4 classic molecules you should be able to draw with your eyes closed. Have a go at their dot and cross diagrams, and then we'll look at them. Okay, carbon dioxide, 2 carbon oxygen double bonds. Count up all the electrons, make sure everything's in the right place. Ammonia, 3 single nitrogen hydrogen bonds and that lone pair of electrons up here where the nitrogen doesn't bond. Ethene, a carbon-carbon double bond in the middle. Now here they've included inner shell electrons for the carbon, but they're not necessary. And then 4 single carbon-hydrogen bonds. And hydrogen chloride, 1 single covalent bond. In general, metallic character decreases across a period and it increases down a group. So if you look at group 4, at the top of group 4 you've got carbon, which is definitely a non-metal. And at the bottom of group 4 you've got tin and lead, which are definitely metals. Okay, have a look at essential chemistry, pages indicated, and answer the questions.